Okay, so welcome back. This is the lecture for chapter 2. Um, let's get going. So, chapter 2 deals with graphing and displaying numbers. Part of this lecture is also going to discuss some of the things that we talked about in chapter 1, particularly some of the basic concepts that we went over, and also some of the levels of measurements that we discussed. So we'll talk about, again, some basic concepts, levels of measurement. We'll see how frequency tables work. We'll see how grouped frequency tables work. We'll talk about histograms and do an example of one. We'll do an example of a polygon and talk about what those are. We'll also take a look at shapes of distributions, talk about the concept of kurtosis and skewness, and we'll touch upon just the beginning of the normal distribution. I say just the beginning because we'll be working with the normal distribution quite a lot this semester. So this is just a brief introduction to it. So some basic concepts. Let's take a look at this scenario here. As part of a larger study, researchers gave a questionnaire to 151 students in a statistics class during the first week of the course. One question asked was, how stressed have you been in the last 2.5 weeks on a scale of 0 to 10, with 0 being not at all stressed and 10 being as stressed as possible? So in this example, level of stress is a variable, right? So it's something that can change. So variables are things that have values that are changeable, that can change, right? So in our example, this is a variable which has values ranging from 0 to 1. The value of a particular person's answer is that person's quote-unquote score. Okay, so things to keep in mind. Values, variables, score. Okay, so a variable, again, is any condition or characteristic that can have different values. In short, it can vary, as the name suggests. Value is simply a number, such as 4, -81, or 367.32. It's simply a number. A value can also be a category, such as male or female, or freshman, sophomore, or senior, or small, medium, large, extra large, so on and so forth. Values don't necessarily have to be numeric per se, right? It depends on what level of measurement we're using. And we spoke about level of measurements in chapter 1, and we'll touch upon that again in this chapter. And a score, as we said, is a person's value on a particular variable. So it's a particular score for an individual on a particular variable. So, reviewing levels of measurement, we spoke about nominal scales. And with nominal scales, each score does not actually indicate a number. Rather, it is used for identification or categorization. So nominal scores only indicate that an individual is qualitatively different from another individual, not necessarily quantitatively different. So when we say qualitatively different, we're saying they're different in some attribute, in some label, or in some category. So in research, nominal scales are used to group or categorize people. So again, for example, something like gender can be used or can be measured on a nominal scale. Things like race and ethnicity, somebody's religion, political party, diagnoses, your work status, so on and so forth. All of these are categorical groups. These are labels, right? Ordinal scales we can think of an ordinal scale as being similar to a nominal scale in that we're still using categories. However, the order in which the categories are placed has some meaning. Take a look at the name, ordinal scales, and the meaning is kind of in the name. These are also referred to as rank ordinal or rank order scales, right? So rank order variables are also called ordinal variables because the variables contain or obtained from these variables can tell us something about their order. So like we said in chapter 1, an example is if you're in a race, a marathon, you will have people who finish in first place, in second place, in third place, so on and so forth. However, the information alone, knowing that someone finished in first place or someone finished in second place, doesn't really tell us about how much time was in between those two places. So ordinal scales lack a consistent interval. And as I said in the last lecture, usually when it comes to races, when it comes to ordinal scales in general, the difference between first and second place tends to be pretty small. And then the difference between second and third place tends to be quite big, and so on and so forth, right? You don't have equal intervals or between these orders or between these rankings. But ordinal scales are still a little bit more informative than nominal scales. Even though we're still dealing with categories, the order in which those categories appear do tell us more information than the categories alone. Interval scales. So we spoke about interval scales, and let me throw up, or well, not throw up, put up ratio, but we'll get to ratio in a second. So interval scales we can think of as ordinal scales, except that the intervals between first and second place, that interval is the same as the interval between second and third and fourth and fifth, so on and so forth, right? So in an interval scale, each score indicates an actual quantity, and an equal amount separates any adjacent scores. So interval scales can include the number 0, but it's not a true 0. It does not mean that none of the variable is present. So when we say it's 0 degrees outside, it doesn't mean that there's no temperature out there. It's almost an arbitrary number, right? 0 degrees Fahrenheit is 32 degrees Celsius, or vice versa, right? I think I got that mixed up. Again, that shows you the arbitrariness of this 0 that exists in these scales. So we can take a look here. As an example, the difference between 75 degrees Fahrenheit and 82 degrees Fahrenheit is the same difference as between 60 degrees Fahrenheit and 67 degrees Fahrenheit, right? So the interval between these numbers is the same. Unlike an ordinal scale, where if you told me someone came in first place and someone came in third place, I would have no idea what the difference was in terms of actual time it took them to complete a race or a marathon there. However, in this example, temperature of 0 Fahrenheit does not indicate a total lack of heat or temperature. In fact, temperatures can be below 0 degrees Fahrenheit. We see this all the time. So that 0 is kind of arbitrary in an interval scale. We should note that it is possible to make quote-unquote ratio statements that compare one score to another. I just said possible. It's impossible to make ratio statements that compare one score to another because we don't have a true 0 point, right? So it might seem that 4 degrees Celsius is twice as hot as 2 degrees Celsius. However, if we measured the same physical temperatures using the Fahrenheit scale, we would have 35 degrees and 39 degrees, right? So in Celsius temperature, 4 degrees Celsius is twice as much as 2 degrees Celsius. But those same temperatures in Fahrenheit equate to 35 and 39, or 39 and 35. So we can't make ratio type of statements. We can't say that this is twice as much as this, right? With an interval scale. We can with a ratio scale. Because in a ratio scale, we do have a true absolute 0. And I made a joke last time that if you were to check my wallet and you would see $0 in there. So amount of money you have is a ratio scale because you could have 0 money. And that's true, right? You can score a 0 on an exam. Let's hope you don't in this class. But you can have 0 points. Can you have 0 weight and still exist? Or 0 height and still exist? Those things, those two examples I gave you are kind of iffy zones, whether or not they are ratio scales or interval scales, because I'm talking in the theoretic. But yeah, in terms of something like weight or height, they might very well be treated as ratio scales because you can say that something does weigh twice as much as something else, right? But if I were to give you a depression scale or a happiness scale on a scale of 1 to 10, and somebody you chose 8 and someone else chose a 4, I can't in good conscience say that you're twice as happy as that person, right? Because I don't know. It's a little bit of a subjective scale, especially if I'm doing a 1 to 10. Even if I threw in a 0 to 10, a 0 is kind of arbitrary because what a 0 happiness is for me might be very different than what a 0 happiness is for you. So ratio scales, when we talk about ratio scales, the scores reflect the true amount of the variable that's present. So the scores measure the true amount. There's an equal unit of measurement, so an equal interval, and 0 truly means there's no amount of that variable there, right? No amount is present. So we cannot have scores less than 0, or we can't have any negative scores on the ratio scale, even though I'm not sure about that, right? Because if you ask about like my net wealth, I got tens of thousands in a mortgage, tens of thousands in student loans. If you ask me how much money I have, I'm probably gonna say negative 80,000, right? Does that mean I have no money? Probably not. I don't know, right? But let's, all jokes aside, and without being hypothetical or getting too philosophical here, some examples of ratio scales might be the amount of calories that you consume. Maybe you didn't eat anything in a day. You consumed 0 calories. That 0 actually means 0. The amount of money that you have. You might be broke, have 0 money. Exam grades, all of these things can be measured on ratio scales because they obtain the true amount. There are equal intervals between the variables, and it's possible to have a true zero, meaning a complete absence of that variable. That being said, interval scales and ratio scales are usually combined. So for the most purposes that you will encounter in psychology or the behavioral sciences, interval and ratio scales are kind of treated similarly, but it's important to understand the difference between the two. When it comes to, again, levels of measurement, any scale can be either continuous or discrete. Continuous scales allow for fractional amounts, so they continue between the whole numbers. So you're able to have decimals. If I gave you a 1 to 10 scale, how happy are you? 1 being miserable, 10 being really freaking happy, and you choose a 4 or 5, I'm not in that scale if I only put 1 to 10 on there. I'm not giving you an option to choose 4.5 or 5.6 or 5.7, right? So when we talk about continuous scales, we're talking about scales that actually allow for decimals in there. Now, the scale that I just referred to, that 1 to 10 scale, we usually see it as a 1 to 7 or a 1 to 9 scale, sometimes a 1 to 5 scale. That's called a Likert scale. It's used in questionnaire research or questionnaire measures for the type of research that we do in psychology. And there's, some serious debate of whether these are really continuous scales, because we don't allow people to choose a 4.5 or a 4.6 or so on and so forth. But we treat them like interval scales or continuous measures. Why? Well, because we're ultimately interested in the means that come out of these scales. So if we're just looking at one individual person, maybe we shouldn't treat it as a continuous scale. But if we're looking at lots of different data from lots of different people and we're comparing means, well, then we will actually get means from these scales that contain decimals, right? So it acts like a continuous scale. But when it comes to, say, a legit example of a continuous scale, something like age can be measured on a continuous scale. It's possible for someone to be 35 or 23 and a half years old. I don't know where 35 came from. I guess wishful thinking. When it comes to discrete scales, they could only be measured in whole number amounts or whole category amounts, right? So no decimals wouldn't make any sense in this regard. So an example would be the number of cars that a family owns, or a child's grade level. These would be discrete variables. So it wouldn't make sense to say you have 1.5 cars, right? Or to say that you're in the 2.75th grade. That's not really a thing, right? However, when we take a look at national statistics about like how many cars an average family owns, something like seeing, the average family owns 1.5 cars, or the average family has 2.5 children. That makes sense to us because on an individual level, it makes no sense because it's a discrete variable. But once we start consolidating this data, those discrete variables can sometimes start acting as continuous variables. Or if not acting, we can at least treat them like continuous variables, meaning that we can start using some of these statistical techniques that we're going to learn throughout this semester on these types of variables, even though it wouldn't really make sense to do so, right? At an individual level there. So when a discrete variable only has two possible levels, we call that a dichotomous variable. So something like a yes or no, or living or dead, or male or female, those would be dichotomous variables. So think of dichotomous or dichotomy meaning two. You only got two options there. So true and false would also be an example of that. If you got a true and false question on exam, that would be a dichotomous question. So dichotomous variables are not always the most helpful. I mean, sometimes, yeah, there are questions that can have a yes or no answer, but most things in life, there's always some room or some shades of gray or multicolors in between those things. Okay, so researchers usually assume that nominal and ordinal scales are discrete and that interval and ratio scales are at least theoretically continuous. And that's where I was going before in terms of talking about if I were to give you a Likert scale, say on a scale of 1 to 7, how happy are you? Well, you don't really get to, you have to circle one of those numbers, right? Some students will actually pencil in 5.5, right? And it's like, well, good for you. You're trying to make this a legit continuous scale. So that's what I mean by theoretically. Like sometimes it's not so clear, whether or not a scale that we treat as continuous is actually continuous. But for the purpose of this class, just roll with it. Don't get caught up in the theory there. Okay, so let's take a look at each of these and let's see, what does the scale indicate? Is there an equal unit of measurement? Is there a true zero? And then we'll take a look at some more examples. So with the nominal scale, we see that the scale indicates quality, right? So we're putting people, or we're putting items into categories. Whatever these values are, they're not numerical values by nature. They're categorical or nominal. Think of nominal names, right? Is there an equal unit of measurement? No, there's really no measurement, right? What's the difference? Numerical difference between sophomore, senior, junior, so on and so forth, like or male, female, right? If we were to measure gender on a nominal scale, is there a true zero? No. And some examples again: gender, ethnicity. Gender, of course, can be measured as a continuous variable, as a continuum. Probably should be now, along with sexual orientation. When it comes to ordinal levels of measurement, what does the scale indicate? Well, it indicates relative quantity, right? So it's kind of like a nominal scale in the sense that we're still having these categories of, say, first, second, third type of place as an example, or something like A, B, C, or D as grades in a class. So there's still a categorical component to them. Is there a equal unit of measurement? No, right? The difference between an A or first place and second place is not necessarily the difference between second place and third place, or third place and fourth place, and so on and so forth. Is there a true zero? No. You can't really come in zero place it is possible, well, even say with a letter grade system, failing the class doesn't mean you have a 0 in the class, not necessarily. Even if you get an E in the class or an F in the class, it doesn't represent a complete lack of a grade. It just means a lack of passing the class. So some examples, again, letter grades, class rank, place in a race or marathon or something like that. With the interval scale, what does the scale indicate? It indicates quantity. How much of this variable is there? Is there an equal unit of measurement? Yes. So the difference between 1 and a 2 on an interval scale is the same as the distance between a 2 and a 3, and a 3 and a 4, and so on and so forth. Is there a true 0? No. In an interval scale, the 0 is pretty arbitrary. It does not necessarily mean a complete lack of that variable. And we see that with things like temperature, right? And we see here an example of an interval scale being a checkbook balance. So does a 0 in your checkbook balance represent that you have 0 wealth or 0 money? No, but I would argue that, yeah, it represents you have 0 money in your checking account. So, that could be a true 0. But this is where we can start getting into theoretical differences between interval and ratio scales. So, what's the difference there? Well, ratio scales also are indicating quantity, and ratio scales also have equal units of measurement, except that in a ratio scale there is a true 0. So a 0 on a ratio scale means there is a complete absence of that variable. Some examples might be weight and height, but again, if we want to get theoretical here, can something exist with 0 weight, right? I don't know. I'm pretty sure we can kind of measure everything. Everything's got some mass to it, right? But what do I know? We're splitting hairs. Interval and ratio scales are usually combined into an interval ratio scale, and they're often treated the same way. Okay, so let's take a look at frequency tables. And frequency tables are a way for us to organize our data or organize raw data in a way that helps us better visualize or better summarize those values to get a better understanding of what's going on. So let's say that, well, I'm sorry, having a little bit of technical problems. There we go. Okay, so the scores that we initially obtain from a study are called raw scores. So these are just individual scores, individual datum that we get from our participants. And these individual scores or these raw scores are often really difficult to interpret. So we make use of descriptive statistics to help us try to make sense of this raw data. So there are several descriptive statistical methods that we can use, and we'll learn about some more of them next week. But the starting point is to simply count the number of times each score occurs in our data set. So the number of times the score occurs is known as the score's frequency, which is symbolized by this lowercase and an italicized f. In most statistical procedures, we also count the total number of scores, which is symbolized by the uppercase N, which is also italicized. And now is probably a good time to tell you that any statistical symbols that we're going to encounter will be italicized, okay? So the total number of scores is denoted by an uppercase N, which gets italicized. So if we have an N of 20, that means that we have a total of 20 scores in our data set. So if we count the frequency of each score in the data, we can create what's known as a frequency distribution. And a distribution is the general name that we give for any organized set of data. So if I say the distribution of scores, just know we're talking about an organized set of data that includes a number of raw scores. So the most common way to organize scores is to create a simple frequency distribution table. So to do so, we'll first make a list down the page of each possible value from highest to lowest. We'll then go one by one through our scores and make a tally mark for each next to its value on the list. We'll see how that works. And then third, we'll make a table showing how many times each value on your list is actually used or actually shows up. So we'll use this as an example. Say we obtain the following exam scores from a statistics class. So these are, say, the exam scores from exam 1 in a stats class. So count them up. We have a total of 18 scores. So we would say n equals 18. Step 1 is to arrange these scores from highest to lowest, and we only want to include the unique scores. So we don't want to include, say, non-repeating scores. So, we don't want to include repeating scores. We only want to include non-repeating scores. So let's just do it. We start off with 98. I'm just going through all of these scores and listing them down from highest to lowest. 91, 90, 87, 85, so on and so forth, right? So we basically took care of step 1. We found each unique score and listed it down from highest to lowest. Step 2 is to make a tally mark for each of these scores next to its value on this list. So we'll go through each of our scores, each of our exam scores. We got 90 there, so we'll put a little tally mark next to 90. 70, we got one of those, put it there. 82, 85, so on and so forth. There you go, we got another 70, so we're going to put another little tally mark. And we don't typically have to do this every time we make a frequency table, but it's usually helpful to, when you first start making these tables, to have this type of tally column here. Okay, so we'll just go through it. We got 98, 80, we got 75, 90, another 90, so we're up to 2 90s, 65, another 70, so to 3, 87, 85, 2 85s there, 90, 80, 65, 80. Okay, so we got our tallies there, right? A tally column. Basically, we're just going through and counting how many times do each of these unique scores show up in our distribution. Step 3 is to then list exactly how many times each value appears. And this should be pretty easy because we have this tally column that we can go by, right? So 98 appears once, 91 appears once, 90 appears 3 times, 87, 1, 85, 2, 82, 1, 83, 85, 1, 73, 65, twice, right? So basically that column that we just created is our frequency column, right? So right here, what you see on the screen right now is a simple frequency distribution. Now, it can get more complicated than this. It will get more complicated than this. But if I asked you to create a simple frequency distribution, there you go. There it is. It's done. Let me just go back to the previous slide so you can see what we did here, right? So, again, step 1 was to list each unique non-repeating score from highest to lowest. Then we created a tally column just to help us keep track of our scores. Then we created another column that just took those tally marks and put them into numerical value. And this became our X column, our scores. And then this column here became our frequency column, right? It became this. All we did is just take out the tally marks there to make it look nice, keep it simple. Okay, so what we want to do is just make sure we have all of our scores, make sure we didn't miss anything, right? So the next step would be to sum the frequencies to make sure that they all up to our total number of scores. And if you remember, we had an n of 18, and when I sum these scores up in this frequency column, I get a sum of 18. So I know I got them all. So we're in good shape so far. Okay. We could also create what's known as a cumulative frequency table. And a cumulative frequency table will basically let you know how many scores exist below a particular score. Excuse me. So, how should this work? Well, again, the cumulative frequency is the frequency of all scores at or below a particular score. So, to calculate cumulative frequency, we just need to add up the frequency of a particular score to the frequency of all the scores that are below it. So let's actually see that in motion to get a better understanding of how that works, right? So it's easiest to start with the last score because there are no frequencies below it. So our last score is a 65, and we know we have 2 of those scores, right? So our cumulative frequency at 65 is just 2. And there's no scores below it, so I think cumulative, remember this is all-encompassing. So at 65, how many scores are at or below 65? Just 2, because that's all we got is 2 scores that are 65. Then we can just add the frequency that occurs for the score of 70. And now we add those together and we have a cumulative frequency of 5 at this point. So remember what cumulative frequency is asking. How many scores exist at or below 70? 5, right? Because we have 3 at 70 and we have 2 below 70, right? And we just do this for each score, moving up. So by the time we get to 75, we're asking how many scores in your distribution are at 75 or below. Well, we got 1 score at 75, and then we got 5 scores below 75. So we're at 6 now, right? And we, again, just move up the table. So by the time we get to 80, we have a cumulative frequency of 9, 10, 12, 13, 16, 17. And remember, we have a total number of scores. We have an n of 18. So the cumulative frequency for our last score should be the same as our total score, right? Because what is it asking? It's saying how many scores in your data set are at or below 98. Well, 98 is our highest score. So all of our scores, all 18 of them, should be at or below 98, right? And they are. There you go. We're just adding them all up for cumulative frequency. Okay, we can also make a frequency table with percentages. So we can calculate the percentages of scores for each value. So we know that we have 18 scores in total. So to calculate the percentage of each score moving up, we would take the frequency for each score and divide it by 18. So all we're doing is calculating a percentage, right? So how do we calculate a percentage? We take a number, divide it by the total number of scores. So to do this, simply take the frequency for a value and divide it by the total number of scores, as I just said. In this case, the number of scores that 60, or the percentage of scores that 65 represents, is 11.11. How do I know that? Well, there are two 65s in our data set, right? That's the frequency. So I'm just going to take 2, I'm going to divide that by 18, and I end up with 0.1111, which proportions are decimals. Percentages, to turn a proportion into a percentage, you just multiply it by 100, right? So we take that 0.1111, multiply it by 100, and we end up with 11.11%. And we could do the same for the next score, which is 70. And 70 appears 3 times in our data set. So what percentage of scores in our data set are 70, right? Well, we can take 3, which is the frequency, divided by 18, and we end up with 0.1666. And to turn that proportion into a percentage, we multiply it by 100. So 16.67, just rounding up, that 0.6666 keeps going on and on. We round up, and 16.67% of our scores are 70s. And we could do this for each and every score that is in our distribution, right? So all we're doing is taking the frequency for each of these scores and dividing it by n to get the percentage. So there you go. We created a frequency table with percentages. So not only do we know the frequency of which each of these scores appear, we also know the percentage of our total data set that each one of these scores makes up. So it looks like 90, 80, and 70 all have the same percentage of, or make up the same percentage of our data set. And that makes sense because they all appear 3 times, right? And all the 1s and all the 2s are going to have the same percentage of, make up the same percentage of our total scores because they all appear the same time, or the same amount of times as well. Okay, so again, just to make sure we got everything and we didn't miss anything and we didn't mess up with our calculations, so it's a good idea to sum this column to make sure that our percentages add up to 100%. Now could be some rounding issues in there, right? So don't worry if you're off by a decimal place or two. That's to be expected, right? Because of rounding errors. Okay, so we could take this a step further and we can create a frequency table with cumulative percentages. And cumulative percentages are also known as percentiles. And percentiles you might actually be somewhat familiar with, because if you've taken any type of standardized tests like the SAT or the ACT, and then the GRE eventually for grad school, your score is typically presented to you in terms of percentiles, and that can be a little bit difficult to understand exactly how did you do, right? Well, if you think of percentiles as cumulative percentages, then you can think of your percentile as representing what percent of people or what percent of scores were at or below my score. So how can we create percentiles? Well, we can again calculate the cumulative percentages of each scores. So how do we do that? By simply adding up the percentages, the same way that we did or created the cumulative frequency graph just a few moments ago by adding up the frequencies as we go. We could do the same now, except we'll be adding up the percentages as we go up the list. So let's start with our first score, 65. If you got a 65, what's your percentile? What's the percentile in the class? Well, it would just be 11, the 11th percentile, or more accurately, the 11.11 percentile, right? So we'll start with the lowest score and just work our way up. By the time you're at a 70 in the class, you're in the 27.77 percentile, meaning that 27.77 percent of scores are at or below your score. Okay? And we can just, again, work our way up for each of these percentiles. Or for each of these percentage columns, we're just adding them up in order to create a percentile. So by the time we get to our highest score of 98, this is the highest score we have in our exam distribution there. If you scored an 98, that means 100% of scores are at a 98 or below you, right? So you want to make sure by the time you reach your highest score, your percentile is at 100% or pretty close, again, because of error, rounding error. It could be slightly off. Don't worry about that for our purposes. Okay, so say you scored an 85 on this exam. This would put you in the 66.66 percentile, which means that you scored as high or higher than 66.66% of people who took the exam, right? So that means by the time you reach 85, a score of 85 on this exam, 66% of scores are at your level or below you. So that's how we would calculate and also how we would interpret percentiles. Okay, sometimes we are presented with a lot of data, and the scores we might have too many scores, or there's a huge range between scores. So if we're talking about scores that range from 0 to 100 on something, this is going to be a really big, long frequency table if you have to list out all scores from 0 to 100 on there. So sometimes it makes sense for us to create what's known as grouped frequency tables, which basically means that instead of presenting each individual score with its frequency and its cumulative frequency and its percentage and its percentile, instead what we'll do is create intervals of scores. We'll create little groups of scores and count those frequencies instead. So in our previous example, we should have included all the scores between the highest score of 98 and 65, even though we didn't really have a bunch of those scores, right? This would have resulted in 24 scores that were listed that all had frequencies of 0 next to them. And that doesn't really help us much. The idea here is to make the data more parsimonious, make it easier to understand, to make it more concise. That would not necessarily do it though, right? So we can take the following exam scores as an example here. So we have a little bit more scores in this case. So not just more scores, but we also see the range of scores. Looks like 63 is the lowest score, and it goes all the way up to 100. So instead of listing all the scores, 102. Sorry, somebody got some extra credit points there. So instead of listing all the scores from 63 to 102, if we did that, we would have a whole bunch of scores with just zeros next to them, no frequencies next to them. So instead of doing that, it is probably best for us to create what are known as class intervals. So how should class intervals work? How do we determine how many class intervals that we should even have? There's no real correct way. There's no way that you have to use in order to create class intervals. But here's some, I guess, guidelines that you can use to determine what's the appropriate way that we should kind of split this data up. You know, should I put 5 scores in a group? Should I put 6 scores in a group? Should I put 10 scores in a group? There's some things that we should consider, let's say. So if there are too many scores that are in an interval, then we kind of lose any meaningful information about the differences between the scores. Let's say if we put all the scores from, we're going to do 20 scores in a class interval, that means if you scored a 60 to an 80, you're all counted as one group. But a 60 and an 80 is the difference between passing and failing, and actually not just passing, but doing okay, doing more than just passing, and, you know, really failing, not even just coming close, if 65 is our cutoff. So an interval of 20 would be way too much. We'd be losing some valuable information there. On the flip side of that is that if our intervals have too few scores, if we only want to have 2 scores in each group, then we kind of miss the point. We kind of miss the point of making these intervals to begin with, right? So there's kind of a trade-off about losing valuable differences between our scores, and on the other hand, presenting our data in a way that is visually helpful, and that is clear and easy to understand, right? So again, these are guidelines, but if we want to try to determine what's the best way to figure out how many scores should go into an interval, we can first find the range of our scores, which means the difference between our highest score and our lowest score. So in this case, we have our highest score of 102, our lowest score is a 63, so we have a range of 39, right? The second step is to decide how many class intervals we want to have. And that's up to you. You can say I want 5, just because that's all that I want to draw out, right? Let's say for our example, we'll go with 10. And typically for say exam scores, 10 might be useful. Say, between an 80 and a 90, we're talking about a class of essentially B's, right? B minuses, B's, B pluses. So maybe for our purposes, we'll go with 10. But whatever, for this example, we're just going to go with 10. So we have a range of 40, or a range of 39, rather. And we decide, let's break that up into 10 groups. And that seems like a nice, even number, comfortable number. So to determine how many scores will actually go into each one of these 10, we simply take our range of 39 and divide it by 10. We take our range and divide it by how many class intervals we want to have. We'll end up with 3.9. We just round that up to 4. So each one will have 10 intervals or 10 groups, and each one of those groups will contain 4 scores. Okay, so let's see exactly how this is going to work. We have our data that I said let's use as an example. So we'll start by listing our class intervals, right? So we will start at 60, and remember, each of these class intervals are going to have 4 scores in it. So our first interval will be from 60 to 63. So it'll include 60, 61, 62, 63. 4 scores. Our next one, our next interval will have to start at 64, and that will also include 4 scores, right? So we'll go from 64 to 67 for our next interval. So 64, 65, 66, 67, 4 scores. And we'll do this until we have all of our scores accounted for, or until we have all 10 of our class intervals there, right? So it's important that your final class includes your highest score, and that your first class interval, what we saw before, includes your lowest score, right? So between these 10 classes here, all of our scores up here are going to fall into one of these 10 classes, okay? So we're just going to go ahead and repeat what we did for the simple frequency distribution, except now, of course, we're using groups instead of single scores. So all of our scores here are whole numbers, and all of our exam scores are whole numbers. But what would happen if you had decimals in here? What if someone scored a 97.5? Well, we know where they would fail. But what if they scored a 99.4 or a 99.6? Do they go in this class interval, or do they go in that class interval? Well, these class intervals have something that are known as real limits. Okay? And we're just going to use, this doesn't have to be any more complicated than just the rules of rounding that we use. Okay, so the real limits for the first class interval, and again, we only need to really worry about this when we're dealing with scores that have decimals. So with the real limit, the first class interval would have real limits of 59.5 and 63.4. Okay, you might say, well, Brown, why? Where'd you come up with that? I'm only using the rules of rounding for decimals, right? So if we had a 90 or I'm sorry, a 59.4, then that would, we round down, right? When we have a decimal from 0 to 4, 0.0 to 4, we round down. 0.5 and above, we round up. So in this case, the real limit for this first interval would be 59.5, and it would end at 63.4. So what if I got a 63.5? Which interval would I go to? I would actually go to the next one. I would be rounded up and be included in that 64 to 67 interval. Why? Because the real limits are 63.5 to 67.4. So we're just, whenever we're dealing with decimals in these raw scores, we're just going to use the rules of rounding to determine which of these intervals they go into. So when we talk about the real limits, we're just noting that, yeah, we recognize sometimes there's going to be decimals, and sometimes we might have difficulty finding out or figuring out which interval those scores should go into. And there you go. Those are the real limits in case you need them, in case you need to remind yourself about the rules of rounding for decimals. Okay? So, now that we have our intervals, we don't really need to worry about real limits here because we're dealing with whole numbers. There are no decimals, but let's keep them there anyway. We'll create a tally column. So this, again, will help us just to keep track that we're getting all the scores. We're not missing any of them. So let's just go through each score like we did for the simple frequency distribution. We'll start with 97, right? So we plop that, we find the interval that 97 falls in, and we throw it in there. 100, we got that there. 80, 92, 72, 100, 67, so on and so forth. We're just going to go down this whole list, make sure that we're putting each of these individual exam scores in their corresponding or in the appropriate class interval that we created. So it's exactly what we did for the frequency distribution, right? So as we did with the simple frequency distribution, we're going to go ahead and create a frequency column. And again, that's denoted by this lowercase italicized f. And we just, from here, count up the tallies. So for our first interval, we see there's 3 scores that fall in that first interval. Oh, sorry. We might as well start from the bottom, make our way up. So the first interval, starting from the bottom, is 60 to 63, right? And we see we only have 1 score that falls in that interval. So we have a frequency of 1 for that interval. We have 3 scores that fall in the next interval, so there you go. No scores from 68 to 71, so there's 0 there. We got 2 scores in the next interval, 4 scores in the next interval, 3, 2, 0, 1, 1, and 3. So there you go. This is a simple frequency distribution using class intervals, which you'll see we will often use, because writing out, we would have a whole bunch of individual scores there with tons of zeros. I mean, we'd have tons of these scores that have 0 frequencies in them. In this case, we only have 2 class intervals that have 0 scores, so certainly helps to make things more concise and easier to understand. Now, using the method that we learned earlier, we can calculate the cumulative frequency for each of these class intervals. How do we do that? Remember, it's pretty easy. you start with the bottom. I filled it all in here, but you just start with the bottom score, the cumulative frequency, just add it up, right? So for the first class interval, the cumulative frequency is just 1, because that's all that was there. For the next class interval, it's 4. Why? Because there's 4 scores that are at or below this class interval, 3 plus 1. For the next one, the next interval, we're still at 4 because we didn't add any scores. So in this, there's still 4 scores at or below this class interval. And make our way up, right? So all we're doing to create a cumulative frequency column is to just add the frequencies for each class interval. We're just going up, up, up until we hit 15 there. Okay. Okay. We could also calculate the percentage for each of these as we did previously. So again, I'm not going to repeat that and bore you to death here. But it's just the same as we did for the simple frequency distribution. We'll take each one of those frequencies and divide it by the total number of scores. So then we get the frequencies, the percentages for each of these intervals here. And then we can calculate percentiles as well, because percentiles are just cumulative percentages. I'm sorry. Starting to, my brain's starting to shut down now. But we can calculate percentiles, right? Remember that percentiles are just cumulative percentages. So we're going to do exactly what we just did in order to calculate cumulative frequencies. Remember, to calculate cumulative frequencies, we just added those frequencies as we went up. To calculate percentiles, all we're going to do is add the percentages up, right? So percentiles are cumulative percentages, essentially, right? So there you go. So by the time your score is in the 100 to 103 interval, you're in the 100th percentile. That means 100% of scores are in your interval or below you. Now, you might need to watch this a couple times, or read through your textbook a couple times to fully get, everything that we did here. But it's really not complicated. So just watch it a couple of times just to make sure that you fully grasp each of the steps. A couple of steps that are involved, and maybe on the first go, it might seem complicated, but if you watch it a few times, you'll see that it's actually not just really basic math there. And maybe it could be helpful for you to actually write out each step one by one. Okay, so let's talk about histograms and charts and some displaying of data in a second or part 2 video for this lecture, just so you can get a little bit of a break, because that was kind of a lot of information and a lot of stuff going on that screen that maybe you need to take a break now, and then we'll come back to graphing data. Okay, so I'll see you in a bit.